In this experiment, the behavior of propellant sloshing inside a container was calculated using Ansys Fluent. Primarily, a cube satellite was used for analysis. As a basis for the experiment, a guide on two liquids sloshing within a cup at a frequency of 1 Hz and a maximum displacement of 50 millimeters was used. The graphs on the right depict the volume fraction of liquid in the cup and the mixing of these two liquid layers right below it. For the cube satellite, 3 CFDs were made with dimensions of 10 by 10 by 10 centimeters, or 1 unit. The CFDs were made to have a liquid domain of 40%, 50%, and 60% of the total cube's volume respectively. These CFDs were converted into meshes using Ansys, each having a resolution of 7 and nearly 200,000 elements. The initial setup for the Fluent solver subjected these cubes to STP conditions, with the propellant liquid domain being comprised of water and the rest being air. Unlike the guide, the top was closed off from the atmosphere and a surface tension coefficient of 0.0075 newtons per meter was introduced. This helped the floating point errors decrease and realistic behavior increase. Each initial volume condition was subjected to 1 Hz, 10 Hz, 60 Hz, and 120 Hz oscillations with a maximum displacement of 50 millimeters. The acceleration equations for which are listed below. Each trial showcases 0.5 seconds of fluid behavior. At 40% water volume, an increase in frequency is shown to increase the rate at which the water and air mix, becoming increasingly turbulent. At 50% water volume, the same phenomena is observed but with even quicker mixing and increased turbulence. 60% water volume follows the last two trends and showcases the highest rate of mixing and induced turbulence. With all trials side by side, the effect is better visualized. Interestingly, it can be seen that over the 0.5 seconds, the water volume fraction decreases. This can better be seen with a close-up of the 40% volume 10 Hz trial. With this, it can be inferred that if allowed to propagate further in time, the higher frequency cases might assume a state more similar to the 10 Hz cases where everything is evenly mixed. In the aerospace industry, even the evenly mixed fluids can reduce in the potency of the propellant and cause air to be injected alongside it. A common issue with propellant sloshing is that it can cause unwanted pressurization and depressurization of the propellant tank due to varying wall temperatures coming into contact with the propellant and causing the liquid to be away from the injectors. This is commonly mitigated using ullage motors to force the propellant to one side of the tank. Thank you.